Hi everyone, today I'm going to teach one important idea in probability, conditional probability, and then we'll use it to understand Bayes' theorem. The title is From Clues to Chances, because many real probability questions are not about guessing from zero. Usually we already know something and then we receive a new clue. After that clue appears, the probability can change. In this lesson, our main question is, how should we update a probability correctly? By the end of this short lesson, you should be able to do three things. First is read the formula on the right side as the probability of A given B. Second, identify the correct denominator or the correct group we are counting inside. Then use a simple Bayes example to interpret a result in real life. And then we'll use a medical screening test as our main example. Let's start. 什么鬼 Okay. Let's begin with a quick question. Imagine a test says positive. What is the chance that the person really has the condition? On the slide, answer A says about 95% because maybe the test is very accurate. And answer B says much lower because positives can include false alarms. If you were my students in class, I would ask you to vote now. Please choose A or B in your mind. Do not worry about being wrong. The question is designed to feel a little bit tricky. Okay, many of you may naturally choose 95%. That answer feels reasonable because if a test sounds accurate, we want to trust it. But in probability, we must be careful about the direction of the condition. The chance of a positive test if someone has the condition is not the same as the chance someone has the condition if the test is positive. That difference is exactly what we need conditional probability. So here is a definition. Conditional probability means shrinking the word first. The formula is give the probability of A given B is like this formula. We read this as the probability of A given B. The important phrase is given B. It means B has already happened or B is already known. So we do not count the whole universe anymore. We only count inside B. As you can see in the diagram, B is the right circle inside that circle. Some cases are also in A. That overlapping part is P and A, probability of P, A and B. So the denominator is probability of B. Because B is the condition, the numerator is probability of A and B. Because we want the part of B where A is also true. In plain English, we ask among the cases where B happened, how often did A also happen? This is key habit for the whole lesson. Condition first, then count. A two-way table is one of the easiest tools for conditional probability. Look at this example. There are 150 students in total. So some take the bus, some walk, so some arrive on time, and some are late. Suppose I ask, what is the probability that a student is late? Given that the student took the bus, the phrase given that the student took the bus tells us the condition. So we only look at the bus row. In that row, there are 90 bus students in total. All of the 90, 18 are late. Therefore, given the condition that that students took bus to school, and the probability of the students being late is equal to 18 divided 90, which is 20%. Notice that we did not use 150 as the denominator. if we use that number, we would answer a different question. The probability that a randomly chosen the students is both late and a bus student. But the question says we already know the students took the bus. I hope this table can help you avoid mixing up these questions. Now let us return to the medical screening example. Suppose we test 1,000 people. Only 1% of people have the condition. That means 10 people have it, and 990 people do not have it. This starting percentage is called the base rate. It is the probability before the test result appears. Now suppose the test behaves like this. If someone really has the condition, the test is positive 95% of the time. This is called sensitivity. But if some does not have the condition, the test is still positive 10% of the time. That 10% is the false positive rate. Here is the surprising part. The group without the condition is huge, 990 people. So even a 10% false positive rate can create many false positives. This is part of the problem. A positive result does not come from people who truly have the condition. It can also come from people who do not have the condition but still test positive. So Bayes' theorem helps us reverse the condition carefully. The formula on the slide is given condition B, the probability of A, which is equals the given the probability of B given A and 乘上 probability of A, then divided by probability of B, the left side. The probability of A given B is what we want. In our example, A means has the condition and B means test positive. So we want the probability of having the condition by giving the test results positive. The numerator has two parts. The probability of B given A is the chance of a positive test. If the person truly has the condition, probability of A is the base rate, or how common the condition is before testing. The denominator probability of B means always the evidence can happen for a positive test. That includes true positives and false positives. The useful sentence is posterior equals evidence genesis times prior divided by total evidence. The posterior is the updated probability after we see the evidence. Bayes' theorem can look abstract, so natural frequencies make it easier. Start with 1,000 people. Since the base rate is 1%, so 10 people have the condition and the other 909 do not. For 10 people who have the condition, 95 test positive, that is 9.5 people. The left test negative. For the 990 people who do not have the condition, 10% still test positive. That is 99 false positives. The other 891 test negative. Now focus only on positive test results. How many positive results are there in total? There are 9.5 true positives plus 99 false positives, so there are 108.5 positive tests results. This number is the denominator for our question. We are not asking about all 1,000 people anymore. We are asking about people who tested positive. And among those positive results, only 9.5 are true positives. So now we can calculate. Given the probability of of having the condition giving the test results positive is equal to 9.5 divided by 95 plus 99. That is, the result is about, as you can see, 8.8%. This is why the warm-up was tricky. The answer is not 95%. A 95% sensitivity tells us the probability of test result positives, given having the condition. But the question asks about probability of having the condition by giving the positive results. And those are reverse conditions. The result doesn't mean the test is all useless. A positive result still gives important evidence, but it also does not mean we should jump immediately to certainty. In a real medical situation, this would usually mean follow-up testing and professional interpretation. So the mathematical lesson is, when the condition is real, false positives can dominate the positive group. So let us change only one thing: the base rate. The test is still seen. If someone has condition 95% test positive, if someone do not have the condition, 10% still test positive. In scenario 1, the condition is real, is 1%. We already found that the probability of having the condition giving the results positive is about 8.8%. And in scenario 2, suppose the condition is more common, 10%. Out of 1,000 people, 100 has the condition and the 900 do not. From the 100 people with the condition, 95 test positive. From the 900 people without the condition, 10% test positive. So 90 people are false positives. Now the positive group have 95 true positives and 90 false positives, for a total of 185 positives. So the probability of having the condition given the test results is positive is 95 divided by 185, which is about 51.4%. The test did not change, but the base rate changed, and that changed the final probability sharply. Base updating is not a formula. It's a way of thinking about evidence. In medicine, a screening result can suggest whether follow-up testing is needed. In spam filters, certain words, links, and sender behavior update the chance that an email is a spam. Or in weather forecasting, clouds pressure and the radar update the chance of rain. In all of those examples, new evidence changes what is reasonable to believe, but it does not usually create absolute certainty. So Bayes help us avoid two mistakes. One mistake is ignoring the evidence. The other evidence is overreacting to evidence. Good probability thinking stays between those extremes. So let us check the main ideas. There are 3 questions, and if you can answer these 3 questions, I think you may understand the core idea of this lesson. So the first one questions: in the formula, the probability of A given B, which group is the dominator? The answer is A, all cases where B happened. B is the condition. And in the answer of the question 2 is because false positives may outnumber true positives, especially when the condition is rare. And for the question 3, the base is used for updating a probability after evidence. So, finally, we can finish with one sentence. Condition first, then update. Starting with prior probability. Observe evidence. Count always the evidence can have happen. Then compute the updated probability. Conditional probability tells us to count inside the condition, and Bayes' theorem tells us how to update when the condition is new evidence. So the next time you see a probability question with the word given, you can pause and ask, what group am I allowed to count inside? That question would guide you to the right denominator, the right calculation, and a much better interpretation. Thank you.